The e-bike market is now worth around $47 billion, with over 60 million units sold worldwide. But here is the problem most buyers do not see until it is too late. Many modern e-bikes look perfect in the showroom: sleek frame, hidden battery, phone app, smooth motor, and a premium price tag. Then one warning light appears, one battery error hits, or one system locks out, and the rider is stuck with a heavy bike they cannot fix. For people who paid over $3,000, that is not a small problem. It is a broken promise. Modern e-bikes are being sold as freedom machines, but many are built around locked parts and dealer-only repairs. That is why 90% of them may not be built for real riders. To understand how we got here, we need to examine the transformation of the bicycle industry over the past decade. Traditional bike manufacturers like Trek, Specialized, and Giant spent over a century perfecting mechanical systems: derailleurs, brake cables, and steel frames that could be repaired in any shop with basic tools. A quality traditional bicycle could function for decades with minimal maintenance. The electric revolution changed everything. When lithium-ion batteries became affordable enough for consumer applications around 2015, established manufacturers faced a choice. They could engineer robust, repairable electric systems, or they could embrace the planned obsolescence model that had proven so profitable in consumer electronics. The industry chose planned obsolescence. The shift began with battery integration. Early electric bikes used removable battery packs mounted on rear racks or frame tubes. These systems allowed easy replacement, upgrade, and off-bike charging. Riders could remove the battery for security or charge it at their office desk. More importantly, when the battery eventually wore out, replacement cost $200 to $300 rather than requiring a complete bike replacement. Modern electric bikes have deliberately eliminated this flexibility. Integrated batteries are now hardwired into custom frame cavities, sealed with proprietary connectors, and protected by digital rights management software. Manufacturers claim this integration improves aesthetics and theft protection. The real motivation is economic control. When an integrated battery fails, which happens predictably after 800 to 1,000 charge cycles, the replacement process requires specialized tools, software access, and dealer intervention. This typically costs $1,500 to $2,000, often more than the bike's residual value. The engineering ensures that battery failure equals bike replacement. Battery chemistry reveals another layer of deliberate limitation. Lithium-ion cells are available in multiple configurations, each with different performance characteristics. Lithium iron phosphate cells offer exceptional longevity, withstanding 3,000 charge cycles while maintaining 80% capacity. Lithium, nickel, manganese, cobalt cells provide higher energy density but degrade significantly faster. Market analyses confirm that over 90% of consumer e-bikes use NMC instead of heavier, longer-lasting LFP chemistry. While NMC reduces overall bike weight and increases energy density for better range, its cathode degrades significantly faster. Manufacturers prioritize immediate aesthetic and weight metrics over the superior long-term cycle lifespan of LFP cells. Motor selection follows similar patterns. Hub motors and mid-drive motors represent two distinct approaches to electric bicycle propulsion. Hub motors integrate the electric motor directly into the wheel hub, providing simple, reliable power delivery. Mid-drive motors mount at the bike's bottom bracket, allowing the motor to work through the bike's gears for improved efficiency and climbing ability. High-quality mid-drive motors from companies like Bosch, Shimano, and Bros can operate reliably for 5,000 to 7,000 hours. These motors feature robust bearings, effective thermal management, and repairable components. However, they cost manufacturers $300 to $500 per unit. The majority of consumer e-bikes instead use cheap hub motors manufactured in overseas factories with minimal quality control. These motors typically fail after 12 to 1,800 hours of operation. Bearing races wear irregularly, windings overheat, and internal controllers fail without warning. replacement requires wheel rebuilding and often frame modifications, making repair economically impractical. Software lockouts represent perhaps the most egregious example of anti-consumer engineering. Modern e-bikes incorporate sophisticated computer systems to manage motor assistance, battery charging, and safety features. These systems could operate as simple, reliable interfaces between human input and mechanical response. Instead, manufacturers have weaponized firmware to enforce artificial limitations. Diagnostic codes prevent operation when the computer detects unauthorized repairs or modifications. Speed limiters cannot be adjusted even for legal off-road use. Battery charge algorithms intentionally reduce capacity over time, forcing premature replacement. Many modern e-bikes utilize closed CAN bus ecosystems where motors, batteries, and controllers are cryptographically paired. For example, Bosch motor systems require proprietary dealer diagnostic tools simply to clear basic error codes or enable a hardwired headlight. These digital restrictions heavily limit independent mechanics and actively harm the long-term rider experience. The European Union's updated battery regulation, heavily enforced by 2026, specifically addressed these practices by mandating that light transport batteries remain removable by independent professionals. However, outside European jurisdictions, manufacturers continue leveraging diagnostic software to restrict independent access and repairs. Consumer advocacy groups have documented the real-world impact of these design decisions. The Bicycle Product Suppliers Association found that the average electric bike requires professional service intervention 6.3 times per year, compared to 1.1 times for traditional bicycles. Service costs average $840 annually, often exceeding the bike's original purchase price within 3 years. Frame design has also suffered under profit-first engineering. Traditional bicycle frames use standardized components that allow extensive customization and repair. Bottom brackets, headsets, and dropouts follow industry standards that have evolved over decades. A mechanic can service these components with standard tools and readily available replacement parts. Modern e-bike frames increasingly use proprietary standards that lock riders into manufacturer-specific replacement parts. Custom bottom bracket threads, non-standard brake mounts, and unique cable routing prevent cross-compatibility with standard bicycle components. When these proprietary parts fail or wear out, replacement requires manufacturer approval and often involves extended waiting periods. Certain cargo models, like early iterations of the Radwagon, utilized unusually oversized rear rack tubing that prevented standard bicycle child seats from mounting securely without adapters. Owners often felt pressured to purchase proprietary accessory systems, which cost significantly more than equivalent standard components and lacked cross-compatibility. Charging infrastructure reveals another deliberate limitation. Electric bikes could easily use standardized charging systems that work with common power adapters. USB-C power delivery already supports the voltage and current requirements for most e-bike batteries. Standardized charging would allow riders to charge at coffee shops, offices, or public charging stations. Instead, every manufacturer uses proprietary charging connectors that only work with included power adapters. These adapters frequently fail, especially the inline transformers that generate significant heat during operation. Replacement adapters cost $100 to $150 and often require direct manufacturer ordering. Lost or damaged chargers effectively disable the bike until replacements arrive. This artificial dependency generates substantial aftermarket revenue while providing no technical benefit to riders. The engineering deliberately prioritizes manufacturer profit over rider convenience. Brake systems demonstrate how cost-cutting compromises safety. Mechanical disc brakes provide reliable, adjustable stopping power with minimal maintenance requirements. Cable-operated brakes can be serviced with basic tools and standard replacement parts available at any bike shop. Quality mechanical disc brake systems cost manufacturers $30 to $500 per bike. Several budget e-bike brands use unbranded mechanical calipers with proprietary mounting brackets or irregular pad shapes that fade quickly under electric operation. Replacement pads are frequently only available through the manufacturer's direct supply chain, costing substantially more than equivalent standard Shimano or SRAM pads available at any shop. Tire and wheel specifications further limit rider options. Standard bicycle wheels use consistent hub spacing and axle threading that allows tire and wheel swapping between different brands and models. Riders can upgrade to puncture-resistant tires, different tread patterns, or seasonal configurations as their needs change. Electric bikes increasingly use non-standard wheel specifications that prevent this flexibility. Custom hub spacing, proprietary axle systems, and unusual tire sizes lock riders into manufacturer-approved replacement parts. When these specialized tires wear out, replacement costs 2 to 3 times more than standard bicycle tires and often involves extended shipping delays. The implications extend beyond individual frustration to broader environmental and economic concerns. The bicycle industry markets electric bikes as sustainable transportation alternatives to cars. However, the planned obsolescence engineering creates massive electronic waste streams and forces frequent complete unit replacement rather than component-level repair. A traditional quality bicycle can operate for 20 to 30 years with basic maintenance and occasional component replacement. The total cost of ownership, including purchase price and maintenance, typically ranges from 10 to 20 cents per mile over the bike's lifetime. Current electric bikes often average 3 to 5 years of useful life before major closed system failures make replacement highly expensive. The total cost of ownership, factoring in rapid depreciation and proprietary battery replacements, can exceed 30 to 5 to 0 cents per mile. This cost structure makes intensive e-bike ownership significantly costlier than traditional bicycles. The repair industry has responded by developing unauthorized workarounds for manufacturer restrictions. Independent shops now offer battery cell replacement services, motor rebuilding, and firmware modification to remove artificial limitations. However, these services operate in legal gray areas and often void manufacturer warranties. Some manufacturers have begun pursuing legal action against repair shops that offer unauthorized services. Specialized recently filed cease and desist orders against 3 California bike shops that offered independent motor repair services. The company claimed that unauthorized repairs violated intellectual property protections and compromised rider safety. Rather than high-profile lawsuits, manufacturers enforce these restrictions through aggressive dealer agreements and strict warranty policies. Major motor suppliers like Bosch and Shimano explicitly prohibit the opening or servicing of internal motor components by independent mechanics. If a local shop attempts an unauthorized bearing replacement or internal repair, they risk being permanently locked out of the manufacturer's proprietary diagnostic software network, effectively ruining their ability to service that brand. Brands also frequently rely on broad void-if-tampered clauses, heavily discouraging consumers from seeking third-party mechanical help despite the legal consumer protections outlined in the Magnuson-Moss Warranty Act. Overseas, regulatory bodies are actively forcing a shift in how these expensive machines are engineered. The European Union's Eco-Design for Sustainable Products Regulation, or ESPR, directly targets planned obsolescence by penalizing the digital software lockouts designed to prevent component-level repair. This new legislation also mandates the implementation of a standardized digital product passport for all light transport vehicles by 2027. This mandatory digital ledger forces e-bike manufacturers to publicly disclose full fault codes, battery chemistry life cycles, and exact repairability and long-term durability metrics before a bicycle can legally enter the regulated European market. European manufacturers have taken a different approach. Companies like Risu and Mueller, Kalkoff, and Gazelle prioritize repairable designs with standardized components and available replacement parts. These bikes typically cost more initially but offer significantly lower total cost of ownership through extended useful life and reasonable repair costs. The Risu and Müller supercharger uses standard Bosch motor systems, removable batteries with standard connectors, and frame components that can be serviced with conventional bicycle tools. The company provides detailed repair manuals and sells replacement parts directly to consumers. Independent testing shows these bikes maintain over 90% functionality after 5 years of regular use. However, these European models represent less than 8% of the global e-bike market. The majority of consumers purchase from major American and Asian manufacturers who prioritize short-term profit margins over long-term customer satisfaction. Consumer advocacy organizations recommend specific features that indicate repairable, durable e-bike design. Removable batteries with standard connectors, motor systems from established manufacturers like Bosch or Shimano, and frame designs that use industry-standard components all suggest better long-term value. Buyers should specifically avoid bikes with integrated batteries, proprietary charging systems, or unusual component specifications. Smartphone app requirements, especially those requiring constant internet connectivity, typically indicate software lockout capabilities that will limit future flexibility. The electric bicycle industry stands at a crossroads. Consumer awareness of planned obsolescence practices is growing, driven by social media documentation of premature failures and repair restrictions. European right-to-repair legislation is expanding to include more product categories, potentially affecting bicycle manufacturers who sell in European markets. Manufacturers frequently defend these closed hardware ecosystems by citing rider safety and the documented threat of battery fires. Following multiple high-profile lithium-ion battery incidents, municipalities like New York City implemented strict regulations such as Local Law 39, requiring all e-bikes sold to meet Underwriters Laboratories 2849 certification. While these rigorous safety standards are critical for preventing thermal runaway in unregulated imports, major manufacturers also use these compliance requirements to strictly limit independent repair options. Bicycle brands argue that unauthorized third-party interventions, specifically replacing individual power cells or bypassing the battery management system, compromise the original UL safety certification and shift legal liability. By tightly coupling software diagnostics with hardware validation, they mandate that consumers purchase entirely new, factory-certified battery packs at premium prices rather than allowing independent electronics technicians to perform internal refurbishments. This strict enforcement of safety certifications effectively restricts the independent repair market. The environmental toll of this engineering approach is measurable. Battery recycling consortiums estimate that millions of micromobility batteries will reach a premature end of life by the end of this decade. Because proprietary digital locks make these battery packs economically unviable to refurbish, functional lithium-ion cells are frequently sent directly to energy-intensive shredding facilities instead of being reused. While these recycling centers successfully recover raw metals, destroying functional cells forces materials back to the beginning of the manufacturing cycle, contradicting the sustainable transition promised by the e-bike industry. Consumer rights organizations like iFixit have extended their right to repair advocacy from smartphones to electric bicycles, demanding transparent, standardized repairability scores at the point of sale. Recent legislation like California's Right to Repair Act, Senate Bill 244, established a framework compelling consumer electronics manufacturers to provide replacement parts, tools, and schematics to consumers. However, until these laws explicitly expand to cover the specific micromobility sector, manufacturers maintain tight control over the intersection of digital copyright and physical ownership.